Hi, folks. I believe at the beginning of the last lecture video, I misspoke and said that was number 6, but in fact, this one is number 6, designed to kind of give you an overview of what's in the 6th assignment on on our My Math Lab site. So what is that? Well, basically ironing out our understanding of the logarithm function, and thinking a lot about features of its graphs. I say graphs because, well, there's a lot of them, right? Every different potential exponential thing with a b to the x has a logarithm function with a subscript b on the log thing. All right, so we're gonna do most of this in GeoGebra. Let's do that now. The features we're going to want to see are basically a couple of points that are always on the graphs of a log function. Let's go ahead and insert the logarithm graph, and I want the logarithm to the base b, so I'm choosing that version that has the subscript thing, and we're going to put it in as a letter, and then x is the variable, and hit go. So it created a slider for us for b. Now, one thing I'm going to, well, the value 1 is a little bit of a strange logarithm because, well, 1 would be a strange base for an exponential. If you were raising 1 to the x, you're just always going to get 1. So maybe not 1, but some other value a little bit different from 1 makes sense. So that's a typical logarithm curve. Some things we need to recognize. Well, actually, before I do that, let me put on at the same time the graph of the corresponding exponential, which would just be b to the x power. Right? And of course, those two graphs have the symmetry where they're reflections in line y equals x. I think we can leave that line off for now because you can see it. One thing that is always going to be on that exponential graph is the point I'm trying to hold my cursor over right now. It's the y-intercept of the thing. It's the point 0, 1. Might as well put it into the algebra thing so that it actually plots it and keeps it there for us. Now, because we've got this exponential and its corresponding logarithm, inverse function, there's also a point that's always on the logarithm, and I'm pointing at it right now. Now that, notice the difference between the way they call those things. Oh, well, now that I put the point there, I can't click on it anymore. But GeoGebra identified that there was a y-intercept here. On this spot, if you click on it, it tells you it's a root. Still, let's put it in there, 1, 0. So my claim is that those 2 points are going to be visible, and they're going to be the same no matter what our base is. So let's try sliding this slider around. Oh, you know, one thing I want to do before I go too much farther is change the setup on that slider. For changing a lot of features of any one of these graph elements, you have this triple dot thing here that pulls up a menu. And if you pull up settings in that menu, it pops in from the side over here on the right. There's a lot of different things that you can do to affect the appearance of a thing. In particular, for the slider here, we want to be able to change the min, the max, and the increment. So what is a reasonable min and max? I just saw that b equals 1 didn't make much sense, but the smallest value that is okay is actually smaller than 1, and then values larger than 1 are cool too. So we're going to have to sort of pass over 1 as we go. The range I'd like to have us do for this slider is from 0 to, say, 10. And let's make an increment of 0.1. This basically means each pixel on the screen is worth 1/10 of a unit. I don't know if I needed to hit enter on that, but notice how the settings have changed over here on the slider now. The smallest value is 0, the biggest value is 10. I'm going to kill out this properties window, and And now we'll play with the b. I'm curious if people will understand why I don't want to go smaller than 0. Why do we not have negative numbers in there? Actually, wow, it looks like 0 is kind of goofy too. Yeah, because if the base of an exponential is 0, what's 0 to the x? 0 to the anything is just going to be 0. So you get a little bit of a strange behavior there. At every x value, you get the value 0. And then for the logarithm, you just get this vertical line. If you move the slightest bit away from 0, things do make better sense. So I guess I could have changed that low limit to something like 0.1, but it's really an open interval with 0 at the endpoint. You're just not supposed to go all the way to 0. So that said, what's wrong with negative values? Logarithm based to some negative number. It might seem like a reasonable thing to do. It loses its appeal once you realize what it would mean for the exponential. Because if you were raising a negative number to powers, well, when you're on an even number, a negative number to an even power is always going to be, it'll be positive, but a negative number to an odd power, that'll always be negative. And so if you were looking at like the graph near, say, 100, that's an even power, so you'd have your base to the 100th power, and it'd be positive, be a big positive number. And then you go to 101, and suddenly it's a big negative number. In other words, the graph would have to zoom to super high values and then zoom back down to super low values and back and forth. It would be a truly bizarre looking graph. And so we just normally say, look, it doesn't even make sense to have negative bases in exponentials, so we're not going to have negative bases in logarithms. All right, so for the most part, we're going to be looking at b's that are bigger than 1. Here I've got 1.5. Let's do a particularly nice value, which is 2.0. Now, I'd like you to think about some other points that are on both of these graphs now that we've sort of settled on b equals 2. Maybe I'll switch the screen to the document cam thing so we can do some writing. There we go. So if I made you a table of the exponential function 2 to the x and did it for some reasonable values of x, well, like, how about at -2? Oh, maybe negative numbers are hard. Let's come back to them, but I'm going to go ahead and fill out a nice range of x values here. That one in the middle is easy. What do you get when it's 2 to the 0 power? 1. And this one's easy too. 2 to the 1 power would be 2. 2 squared's not so hard. That's 4. And then this would be 8. The next one down would be 16. I think you've seen that sequence before. Oh, now what about these negative x values? What do we do with those? 2 to the -1 power means 1 over 2 to the 1 power. In other words, that's a half. And that -2 means 1 over 2 to the 2nd. So that one's a quarter. They make the point in the book, and I'm going to remake the point here, that when you have the inverse function for something, you get it by literally taking all these, I shouldn't say you get it. We've got a bunch of points that are on the graph, and we can list a whole bunch of points that are on the inverse functions graph from them. It's literally just switch the x column with the y column. So if I have the log base 2 of x column, that's where you'll see the numbers that are just going in order: -2, -1, 0, 1, 2, and 3. And the x values are these powers of 2 that we were writing down before. So 1 quarter, 1 half, 1, 2, 4, and 8. Literally, we've just switched the 2 columns. A couple of points need to be highlighted here, and it's these 2 that are in the middle. because these two and these two are on every pair of exponential and corresponding logarithm things in a certain sense. Why is that 2 there in that thing? It's because we were raising our base 2 to the first power. And if we're talking about a base b instead of a base 2, that would mean this spot is always going to have a 1, 2, excuse me, a 1b in it. And that means that would be a b in the more general setting too. So we've just argued something that's interesting. 0, 1, and 1b are always on the graph of y equals b to the x. And that means that you can also list some points that are always on the graph of the log function. And they have the roles of x and y switched. So 1, 0, and b1, those guys are always on the graph of, well, no, I just said it. I have to write it now. Always on the graph of y equals the log base b of x. So this actually tells you something, a feature of the graph that's kind of important, or at least you can use it to remember how that feature is going to work out. Before I push onto that, though, I want to have us concentrate on this graph of the logarithm thing. So put this guy back on, and let me take away the exponential part. So we're just seeing the, I guess I kind of don't want to show the point A anymore. I think I've done this a few times, and I hope you recognized it, but if it's not the case, these little toggles to the left of a entry in the algebra view control whether the thing's visible over on the right. So, I can just turn the point B off or on. I guess I like leaving it on. Hey, while we're at it, why don't we put in the other point that I now know is on there, which is b comma 1. That's always on the graph of a log. So I just really confused myself. B1, oh, there we go. New guy called C. But there's a way to do this too. I gotta check and see if I can change the settings on that so that the label is not just the name of the thing, but rather its value. That's what I want. And same thing for this guy. I want the label to not be the name, which is just a randomly chosen letter, but rather the value, which is the point coordinates. Okay, get that out of the way. That looks nicer. So what happens if I change the value of b? Now it really is sort of obvious that just a rescaling is happening. Well, maybe not. It kind of looks like a horizontal scaling is happening, but you know what? It can't be a horizontal scaling. Why can't it be? That point 1, 0, if we were scaling horizontally, it would move, right? Because it's out on the x-axis. Only points that are right on the y-axis would fail to move along if you did a horizontal scaling. So while it may look like, just because this point is moving that way, it's not the case that the scaling is horizontal. It's really vertical, including being able to turn it upside down. Well, let's zoom to that view for a sec. That's the log base 10, or the common log. Unfortunately, I guess I'm so far zoomed out we can't see the, can I go the other way? There we go, there's the point. 10, 1 is definitely on that graph. Now, we talked about asymptotes before, and a lot of people would look at this graph, me included, and say, oh, it looks like it's heading for an asymptote. In fact, right now, it looks like it's heading for an asymptote at 2. Like maybe it's drawing closer and closer to this line, y equals 2. Is it or not? Well, it's not, and here's why. I know when it reaches the value of 2. And anything beyond that, it'll exceed 2. And that happens at 10 to the second power. But we have to go way out there. But if we went way out this way, until we get to 100, 10 to the second power, we will find a spot where we now are bigger than 2. There's 100. If I look at points on this graph, well, I thought it let me click on it and give a point, but it doesn't. Anyway, it's not. It's above that line now. Can I zoom in enough that you see it? Yeah, see how the blue thing is just slightly above the gray line for y equals 2? All right, let's go back to the home view. It doesn't have 2 as an asymptote, but maybe it has 3. It certainly looks like it's curving over, and it eventually will stop rising. But that isn't the case either. In fact, when will it exceed 3? When we're at 1,000, 10 to the third power. When will it exceed 4? At 10,000. So I can tell you where it'll go past any number. If you want to know, when does it reach to 1,000,000? 10 to the million. I know, that's a crazy huge number to even conceive of, but any value can eventually be exceeded if we go far enough out on the x-axis. So no horizontal asymptote. Let's talk about range and domain for a sec. In fact, I guess I'll want to put the graph of the exponential back in. We know the domain and the range for the exponential, at least I hope you do. Is there any x value that will break something that goes of the form b to the x, cause a problem? No. So every single x value is fine as an input. But not every possible y value is actually an output. And you can very easily see it on this graph. If you have a negative number, you get small values. If you have a positive number, you get very large values, depending on the value of the base. But we're looking at 10 right now. But you never get negative values out. So I guess I should record that, which means I want to switch the screens again. B to the x, it has domain, well, I guess I should say that the other way, domain minus infinity to infinity. Right? And its range is the open interval from 0 to infinity. And that has an immediate consequence for its inverse function, because the domain of the inverse will be the range, and the range of the domain of the inverse will be the domain. That is, between a function and its inverse, you just switch the roles of domain and range. So log base b of x, maybe I'll put the therefore symbol here. I use that symbol a lot, so I hope you guys are used to that abbreviation. A triple of dots like that means this is a thing that follows from the previous thing. This is a conclusion. So b to the x has that domain and range. Therefore, log base b has domain 0 to infinity, the range of the other guy, and domain, whoops, wrong, and range, the words don't switch, but the things do. The range is minus infinity all the way to plus infinity. And that is really another very direct way to say, or to see that it can't have a horizontal asymptote. Every actual value is in its range. So there's a point where we get, if it had a horizontal asymptote, there would be a max value up here. It wouldn't go to plus infinity. Okay. The last thing to deal with here is to think about whether the behavior of a logarithm graph. The logarithm we're looking at over here with the logarithm base 10, or logarithm base more generally, some other random b value, it's a pretty obvious feature that this graph is going uphill. It's what we call an increasing function. If you start at any x value and go to a slightly higher x value, the logarithm of that thing will be a little larger. So, like right now, I've got a base, b is 2.5 at, well, that's okay. I could probably do this with a function. Let's try. Suppose I wanted 3 and b to the 3 to be a point. Yeah, that would be on the exponential, wouldn't it? I'm doing this the wrong way around then, aren't I? I want to say b to the 3 and 3. Is that a point on this graph? It is, but you see the x-coordinate is like 15, so it's way over here. As I change the value of b, though, I can probably draw it in closer. Like if I need to make b smaller, don't I? There you go. Now it's visible right on the same screen. Anyway, definitely going up from the one we were looking at, right? We started with this point, go to a slightly larger x-coordinate, you've got higher y values. It's increasing. I want to say this in a, make sure I get the distinction clear to you. You need to think about what happens when x increases, and if y also increases, the x going up makes y go up, then the graph is increasing. You could draw this graph by going this way on it, right? And your pen would be going downhill. That's okay because you'd also be traveling in the negative direction along x. But if you're drawing left to right and your pen is going up, you're talking about an increasing function. So this graph is definitely increasing. And this graph, like, a b-value of close to 8, there, almost exactly 8. I keep missing just by a little bit. It's not worth chasing it. It's also increasing, but not as fast, right? And there's another feature about these graphs that you need to think about. It's not only increasing, but it's increasing at a rate, right? There's an amount that it's going up, and that rate is going down. So we've got something that's going up, and it's always going up, but the rate that it's going up is going down. I'm gonna try to do some mime for you on this. My pen is showing a graph that from my perspective is increasing, and I hope that you're not seeing this in mirror image because that'll be weird. I think you are seeing this in mirror image, so okay, I gotta do it this way. That's an increasing line, right? But this graph, the graphs of these logarithms we're talking about, is going up, but it goes up at a less rate. This angle that the line is that the curve is following gets smaller. That says something about the thing. It's curved, right? If you've got something that's going up, but as you move farther and farther to the right, it gets less and less steep. You can't do that with a straight thing. It's got to be a curved thing. And we can say which way it's curved. Well, you can probably look back at the graph and see which way it's curved. I meant to transition to this view for that whole last little spiel I was doing, but I didn't. Anyway, now I'll go back because this is the moment when we need this view. The graph is curved in a way that's called concave down. Now, what's the deal with concave down versus concave up? If you take a pair of points that are on this graph, and you draw the line segment between them, there's two possibilities. It could be like this graph, where the line between two things would lie above the curve, or it could be like this logarithm curve, where the line connected between them would be below the curve. If your straight line, your line segment connecting 2 points is under the graph, then that's the downward sort of curvature. It looks like a frown rather than the other kind looks like a smile. All right, so we've got an interesting setup here with this b values that are bigger than 1 anyway. The graph is increasing, but it increases at a slower and slower rate. So we end up with a curve. And we already knew this was going to be a curved thing, but there's a kind of an explanation of it. But, well, maybe you saw this flip around behavior before. Remember how 1 was a messed up spot for graphs like this? But if you go bigger than 1, things just changed on us. The exponential is this blue graph, right? And it's, instead of, when b was bigger than 1, it had this asymptote, or asymptotic value along the negative x-axis. Now it's got it along the positive x-axis. And when we were bigger than 1, the logarithm had a tail or an asymptote that went down the negative y-axis. Draws closer and closer to negative y. But when you flip to negative values for the base, that behavior switches as well. So the exponential has the positive x-axis as its asymptote, and the logarithm has the positive y-axis as its asymptote. Also, the increasing and decreasing behavior has changed. The green graph is now going down all the time. Always going down. But, depending on the particular value of b, going down at less and less of a rate. So it's a negative slope along this guy at any point, but it's getting less negative with time. That means it's actually going up, becoming less negative as increasing. Well, anyway, that stuff together tells you that this negative b logarithm graph has got a concave up behavior. And that discussion of increasing and decreasing and concavity is what we really needed to get to the end of for this. So you should have the ammunition you need to do assignment 6. You may also, of course, want to look at some of the other videos. My recommendation is you try the problems and then try to identify which one of the review videos might help you on a given one if you have trouble with it.